Good morning, all. Can you hear me okay? Yeah. All right? Okay. Through Ladder Line and Antennas, would like to welcome you all this morning. And we're hoping we can help solve some mysteries that we all have faced one time or another. I'm Gary, K7EMF. This is Molly, who's our manufacturing manager for the antennas and ladder line. And this is the inventor of the LPS, the Lightning Protection System, Dave, K5OZ. So let's get right to it this morning. So the second half, Dave is going to present the LPS and answer questions that I hope you'll have. One of the things that I hear quite often on the air, and I also have customers fairly often speak to antenna gain. And the consensus is that antenna gain is the all-important factor in developing a good signal. And unfortunately, that is not true. If you can't get the power to your antenna, it doesn't matter how much gain you have, you're not going to have much of a signal. The antenna is going to work, and we know there are all kinds of antennas out there, a lot of variabilities. And so how do we separate the one that really works from all those that do not? And the key is system efficiency. But before we get into that, what is antenna gain? A lot of hams think that antenna gain is where you put X number of watts in and you get 2X number of watts out. That is not true. You don't get something for nothing. So as an example, gain implies that your antenna is directional. In other words, it has a main lobe or main lobes and minor lobes or nodes. You can equate it to this flashlight. Right now, this flashlight has some gain because it has a reflector and also a focusing mechanism that is pointing the beam out in this direction. Now, if I change that and make it more of a point, a tight beam, now I've increased my gain, haven't I? But all around the back of it, there is no light. Same thing with antennas. So if we say that an antenna has gain, then you can count on it having directivity. And therefore, that would imply that we would want to point the antenna, point the main beam in a particular direction. Well, on low frequencies on HF, that's a little bit of a trick, isn't it? I'm not going to be rotating my 240-foot dipole on a regular basis, so how would we steer that? Well, the answer is we do not want to steer it because we pretty much cannot. So the solution is we want an antenna that is nearly omnidirectional for most of us. Now, if you have some DXers that want a beam heading in a certain direction, they might build a large array that focuses in that direction only. But for most of us, we want to talk in all different directions on the low bands like 160 and 80, and sometimes even 40. So, the real issue is system efficiency. And here again, if we don't get the power to the antenna, we're really spinning our wheels. So how do we do that? Let's first of all look, so our goal here is to develop a system that is multiple bands, typically 160 through 10 meters, and also has high efficiency on each of these bands. So the average ham, especially when you first got started, and I fall into that same category, is we'll build a resonant antenna connected with coax, and it works great on the design band, but then I'll say, well, I would like to operate this on other bands as well. So what do? I go out and pick up an antenna tuning unit and feed that, use that to feed the coax, The transmitter sees a nice one-to-one match, but what happens from there? So let's take a look at it. I use an antenna modeling system called SIMNEC, and so when I get calls from customers, I'll use SIMNEC to model their exact system as best I can replicate it. And many of our customers have also downloaded SIMNEC from our website through ladderline.com. They can do the same thing, which is advantageous because if you decide to change your design a little bit, rather than calling me, and that takes time, you can just bring up your own modeling and load in the parameters and away you go. So let's take a look at it. This is where we want to focus is on SIMNEC and how to use it. Can everybody see that okay? You're good? Okay. So this is a Smith chart. You can see my mouse. This horizontal line right here is a divider between inductive reactance and capacitive reactance. So we're all aware that impedance is comprised of resistance and reactance. So above the line is inductive, below this horizontal line is capacitive. The resistive goes along the axis. So if you look over here, these are my building blocks. I have a generator, this would be my transmitter, making 100 watts. And this is my antenna, an inverted V. And that's what it looks like in the design itself. So so right now, and the definition, by the way, of a resonant antenna is where the feed point does not have any reactance. In other words, it's zero reactance. So minus numbers would be capacitive, positive numbers would be inductive. So as we look at, so I can change the length of it right down here. So I highlight it with my mouse. I'm going to use the up and down arrows, and I'm going to change the length of it. Let's see what happens. Now right now, the resultant impedance is right here in the middle, this little blue circle. So I'm going to decrease the length, and look what happens. It goes capacitive, and it goes reactive. And we can see the value of it up here. There's your resistance, 44.9. Reactance is minus 69. So now I'm going to use the up arrow and go in the opposite direction to increase it. Now we're at resonance. And then we move ahead. Now we're inductively reactive. And you can see that our X, or what we call the J ohms, is plus 37. So we're out of resonance. This now is a non-resonant antenna. So when we operate a dipole on multiple bands and even multiple frequencies, that dipole goes from a resonant at the resonant frequency to a non-resonant antenna elsewhere. And further it goes non-resonant, the more reactive it is, and typically the higher the standing waves. So now let's go to a typical installation, especially when we first get our license or thereabouts. We're going to load in a different file. And that one would be this one here. Okay, so now we have a few more building blocks. There's our transmitter again, our generator. This is a differential T tuner. And it looks like that. And then we have the length of coax, 100 feet of LMR 400. And then we're feeding a ballon, in this case a 1-to-1 ballon. And this is our antenna again, same as before. Now you can see, looking right here, that our reactance is close to zero, so that's pretty much a resonant antenna. And if you look right here, you can see the power is 96 watts out of 100 going in. So this system is 96% efficient, quite a good number. So life is good. So now we're going to QSY to 75 meters. Change the frequency right here. Okay, now we have some tuning to do because you see the impedance to the ATU is clear down here in the bottom right. So I'm going to go to the inductors. We have a roller inductor and a differential capacitor. So we'll go to the roller inductor and I'm going to decrease the inductor down, so we're tuning and we're seeing the effect on the Smith chart as we tune. So we're looking at the entire system. Now we're going to tune the capacitor. Back to the roller. And the capacitor. Okay, now we have a resolution. We're presenting 50 ohms thereabouts to the transmitter. You notice our SWR is 1.006, so we have a good resolution. So let's take a look at what's going on with our power levels. So with the W, with the arrow pointing up, we're dumping 1.63 milliwatts out of 100 into the ATU. Look at this coax. We're dumping 84.65 watts into the coax. And then if you look at the resultant to the antenna, 15 watts. So out of 100 watts, we're pushing 15 watts into the antenna. It's kind of bleak. Now this antenna is going to work, but the question is how well does it work? And we'll retune our ATU. We're up close. Okay, so now we have a resolution on 75 meters with this 160 meter antenna, and notice our efficiency is almost 93%. So we're holding up within about 2 points. So we've changed from one band to the other, about a 2-point variation in efficiency. So we have several things to look at here. You notice I've also changed from a 1-to-1 balun to a 4-to-1. So a lot of our customers will say, well, if I buy your antenna and feed line, what am I going to use for a balun? And my answer is I don't know until I model it. So I model it for them, no charge, whether they're a customer or not. And then I'll come up with a solution to which balun they want to use, number one, and number two, the efficiency of their system, so we give them a good idea as to what they're looking at. So SIMNEC is vitally important. A lot of the hams have seen these taboo charts where you shouldn't use a certain length of ladder line or a certain band and that sort of thing. Well, we got away from that because it's way too general. So our only issue here with multi-band wire antenna and high efficiency is, can the ATU resolve the impedance presented to it? Now you notice here we're using 2.09 microhenries of the roller inductor. That's about a tenth of the roller inductor, so we're well within the parameters of the roller inductor, so we know that this will work. But I've had situations where the roller inductors say up at 35 to 40 microhenries. And I got a resolution, but guess what? There aren't any ATUs on the market that can reach that kind of inductance. So the answer is, it's not going to work for them. They will not be able to find a resolution. So they have to know their ATU enough to know what the range is of their components inside, the capacitors and the inductor. So that's how we work it, and there are several ways that we can resolve a situation where we cannot get a good resolution in the range that we want to see. One is changing the feed line length, and we do that also in SimNet. And by the way, this saves us a bunch of money and time and effort by doing all this in the computer. It takes us away from the old days where our best antenna was out in a snowstorm with 2 feet of snow on the ground in the middle of the night, putting up an antenna. That was always my best one. So those days are history. So now we can look at this, and when we get done, we know what we have. We'll have a real good idea as to what we really have designed, which is critical. Antenna length is another tool we have. We can vary the length of the antenna to shift the impedance. Also, we need to keep in mind that anytime, and maybe I mentioned this, anytime we have a high SWR on any feed line, it acts as a transformer. And it transforms the impedance from the feed point of the antenna to some other value. As we change the feed line length, change the frequency, change the impedance of the feed line, that all changes the transformation impedance to something different. So as you can imagine, when we operate from 160 through 10 meters, how are we doing on time? When we change frequencies, QSY, and all these different frequencies and bands, the impedance is going to be all over the place. So we have to come up with a combination of that and the balun, the 4-to-1 or the 1-to-1, that can provide us with a resolution on all the bands that we want to operate. So, would you like to see a real-time demonstration of comparison of the antennas?
Yes. Yes.
Okay. I was hoping you'd say yes. Okay, you can watch this anytime you wish as well. You go to trueladdermine.com and you click on reviews. And the first thing that comes up is TLL versus bazooka, which is a double bazooka. In this particular ham up in northeastern Washington, I gave him, we moved from Washington State to Arizona, and he purchased my tower and beam. When he came to pick it up, I coiled up my wire antenna and ladder line and handed it to him and said, "Tom, take this." And I explained to him why he needed to take it, and he said, "Put it up, and I know you'll like it." And he wanted to know why, and I explained to him a little bit, and he looked at me like, I am just blown smoke. And I figured, well, I'm never going to hear anything on this again. Well, a couple of months later, he calls me on the phone and he says, "Gary," he says, "I put your antenna up," and he says, "I just can't even believe this." And I asked him what was going on. He explained it. I said, "Would you please do a video and send it to me?" Which he did, and that's what this is. So here we go.
Okay, Gary, that is the double bazooka. That is your antenna.
Can you see the view meter?
The non-resident federal ladder line. Now brick down there. Okay, back to the double bazooka. That's the double bazooka. This is why I was having such a hard time hearing everybody on AM. Back to your antenna. That is amazing. I just still am shocked. I'm going to let this video play for a minute. Double bazooka right there. And Brentstone talking. That is almost faded out. And you cut it back to the non-resident antenna fed with ladder line and the 2-inch tower.
All along the road, the little stuff he's going to have to endure, I sure do not envy him anyway.
What a difference.
I'm over there to teach Monday afternoon and leave it waiting for a while.
That might be a long one with Brent talking.
Really?
back to your antenna. And all around the antenna fed with ladder.
Protecting device on the
Both of them up about the same height
then all we
and
have
oriented just about the same direction.
is a good, really dependable power supply.
Matter of fact, the double bazooka is closer to the
The
shaft.
initial one that came from West Virginia will become the spare, so that's what's going.
There's the double bazooka
It's operating that.
right there.
I'll turn it back to you. If you have
And
questions.
then the non-resident. That's the double bazooka. Non-resident title. Amazing. Just amazing.
Okay, so if you wish to have your system modeled, feel free to give me a call or text me, either one, and work through it with you right on the phone if possible. Also, you're certainly welcome to download SimNet, and along with that, you also have the circuit files that will come with it that you can download. So in order to get to that, that would be somewhere up here at the top. SimNet, where are we? Here we go. Well, that's a SimNet demo. Here we go. So this would be the where you copy and paste in your browser this address, and it will get your files will be ready to download right from there. One more thing I would like to point out is that probably aren't going to remember all of this stuff, but we have also a video right here called SimNet Demo. And that one is pretty much a demo of what we
Hi, this is Gary. EMF through ladder line. This morning we're going to take a look at SimNet 2.1. All of you.
So that's about the size of it. I would encourage you, if you're interested, to download SimNet 2.1 from our website. You want to use our website for SimNet 2.1 because there are several iterations since that one, and our circuit files will not work with the newer version, so you want to use. Yes?
I have a question. If you have an infrared antenna, could you talk a little bit, just real briefly, about, there's a discussion about where to put it, if you want to load it, because it's a shorter antenna, the best position to put the coil so you get the maximum radiation of the antenna.
Okay, the question is where would you put the loading coil on an end-fed antenna to get the best performance? First of all, an end-fed antenna is a compromised antenna, and therefore we really don't speak to those much, except that it is a good antenna for portable use. I have one myself, but I think it would probably be wise to go to the manufacturer. There's end-fed half-wave, HW I think is one service setup for doing that, but it is a good question. But the end-fed is a great idea. You have two major problems. One is you have a 49-to-1 transformer, and when you transform like that, your losses go up, and secondly, your counterpoise is very minimal. So you have some serious losses, but it is quite a good compromise antenna, I would say. Sorry, I can't give you a better answer. Any other questions? If you have a desire to order an antenna or a ladder line, we do both 450 and 600 ohm. Give Molly a call. Her phone number is on our website. She deals with all of that. If you have a question about modeling and those sort of things, I try to answer those questions. And also, we will will answer the last question. So I'm going to turn it over to Dave, and he's going to enlighten us on the LPS. Let me get this switched over for you.